happens and the method or the way it happens. We're going to start talking about how we move from reactants to products, and based on which one of those steps is the slowest, that's going to be determining what we refer to as the rate law. So all of this depends on what we refer to as a rate limiting step, right? So sometime, you know, you all know I'm married, I have 2 kids. The rate limiting step for me going anywhere is unfortunately my wife, right? Because she makes sure that I'm ready, then the kids are ready, and then she gets ready. So the rate limiting step for our trip, no matter how far that trip is getting my wife into the car. Once we get my wife into the car, we are good to go, right? There's a whole bunch of other steps, but that's the one that dictates how fast something occurs. All right, so let's look at that in terms of the a chemical reaction. Right? That's where I was just a second ago. All right, so let's look at this. If we have a chemical reaction in which HCl, hydrochloric acid, adds across the double bond of ethene, so this is ethene, and this hydrogen chloride, the HCl, is going to be added across. So one side gets the hydrogen, the other side gets the chlorine, right? When we do this, we can propose the following mechanism, right? So we're gonna go from this overall reaction to a step-by-step process of how this reaction occurs, right? And then we're gonna graph that below, right? In the step 1 of this proposed mechanism, the HCl crashes into the molecule, and one of the carbons grabs a hydrogen, right? Which is gonna make that whole molecule positively charged. And then we are going to have that positively charged run into the negatively charged anion, that Cl, because there would also be a Cl here, right? It's going to run into that leftover Cl, and it's going to form this product. And apparently I can't type because there should be a 2 there, right? That's a 2-step process, right? So if we graph this in terms of energy, we've seen those before. We typically don't look at them in terms of 2 steps, right? We have this energy diagram where we have the energy of the starting material and the energy of the products, right? The reactants to the products, right? And we can go through, in this case, 2 steps. Right? If this is a proposed mechanism as a 2-step, we would see a 2-step energy diagram. Right? And we've already defined some of these processes, like the difference between the energy of the starting material of the reactants and the products. This is, we refer to as delta H of the reaction, right? The distance between this point and the peak of this diagram, this would be the activation energy of the first step. We can have another one here, right? This would be the activation energy of the second step. Right? So if we look at this, the activation energy is a measure of how hard it is for that reaction to occur, right? How much energy do we have to overcome to go from reactants to products, right? This step right here, these would refer to as intermediates, right? And from our mechanism, this would be an intermediate, right? It's there, right? It's something that's formed early in a mechanism and consumed later, right? If we look at this, because this activation energy number 1 is the largest, then we could say that step 1 is the rate limiting step. Because once we get over that hump, right, once this thing comes over this hump, everything else is going to take less energy and therefore should happen faster, right? So we would distinguish that in here as this would be the slow step, right? So our reaction is going to be dependent. As soon as this product is formed, it's going to be almost instantaneously reacted in the second step and go towards product. Okay. So when we talk about these mechanisms now, because we're talking about how molecules move from reactants to products or individual atoms, the molecularity, or how many molecules are involved in those steps, are going to directly relate to the rate, the order, right? So the order is really how many molecules are involved in this step. So if we come up here and we write the rate law for this reaction, we would assume that that is going to be rate is equal to lowercase k times the concentration of HCl raised to some power times the concentration of this ethene raised to some other power, right? If this is the slow step, right, the molecularity of that slow step is going to give us the orders of those, right? So since there's, in this slow step, there's one HCl and one ethane, right? The rate constant is, these are going to be replaced. We can say that the rate of this reaction is going to equal some rate constant times HCl to the first, because in the reaction, the slow step, the molecularity of HCl, the number of HCl's that are reacting is 1. And for the ethene, there's also 1 in that. So our order we look at the overall order, that's going to be 1 plus 1, which is 2. Right? First order with respect to HCl, first order with respect to the ethane, because both are involved in our rate limiting step, or before the rate limiting step. Right? If there was a step 0, for example, there was something that happened before, we would have to take that into account as well. But the rate limiting step and the things that happen before the rate limiting step are always going to be directly related to the molecularity of our, or the order of our rate constant, okay, or our overall reaction. Okay, so with that in mind, this molecularity, how do we get a rate order of 0? Somebody tell me how we would get a rate order, a rate with respect to a certain compound of being 0. How would that happen? So how do we get a rate order of 0? Based on the way we calculated these two values. Anybody? How would we get a rate order with respect to a species to be 0, a specific reactant?
Changing the concentration of the reactant wouldn't have any effect on the rate.
So that's what it means to have a rate order.
Yeah.
But how do we get one? Why, if the mechanism, see if my thing catches up. If the mechanism, the step-by-step, tells us how the the molecules are going from reactants to products in a step-by-step motion, and the slow step, the molecularity, the number of those species that are reacting in the slow step or before, determine the rate law, how would a species have an order of 0? in order for it to be 0, it means that the molecule is involved after the rate limiting step. So if we had a three-part, or if this was the, so if whatever reactant occurs in a step after the rate limiting step, that's still going to be involved in the rate law because it's a reactant, right? But the order is going to be 0 because its concentration or presence has no direct effect on the rate. This is also why, because everything that happens before this rate limiting step, right, if there is where we can get non-whole number rate constants, right? Because we might have to do some substitutions if it's a more involved rate. Right? Okay, so let's go back to this. What is this overall reaction, exothermic or endothermic? This is sort of a review of because we are losing energy, right? The products is less than the reactants. This is going to be an exothermic reaction, right? Because this delta H is going to be a negative number, right? Products minus reactants is, a positive number. Means we're going to get energy out, so it's going to be exothermic. All right. And the last thing I want to review is that we've talked about applying this mechanism in terms of, for a rate equation, 2 sort of steps that are necessary for a mechanism to be considered correct. Right. The first is that the sum of the reactions. So if we added this reaction up, right, the intermediates cancel out, should give us the overall reaction. That's one criteria. The second criteria for a mechanism to be considered potentially viable is that the rate determining step, the slow step, has to give us the observed rate law. Right? Because all of these rate laws are determined experimentally, we can determine this separate from the actual mechanism. Right? So we always determine the rate law first, see how fast the reaction is going, and then determine or propose a mechanism for how that reaction is occurring. And the very last thing that we want to talk about is how a catalyst is going to affect this, right? So we can define a catalyst within a mechanism because it's there at the beginning of a process and is reformed later in the process. So it's technically not in the overall reaction, excuse me. Right? But what it's going to do is, because it's involved in the mechanism, right, it is going to change this picture. And it's going to make it faster because it's going to change it so that the mechanism takes a different path that is lower in energy. Right? So we change EA1 to a lower using a catalyst. So the catalyst themselves is not necessarily involved in the overall reaction, but it's going to change the way that reaction goes from reactants to product by lowering the activation energy of at least one of them, primarily the rate limiting step. Any questions? We have about these mechanisms or the involvement of a catalyst.